I'm Joel Johnson from Ohio State University, here to talk about a new instrument that's kind of at an earlier stage than some of the other talks we've heard about in this session. Give an update on where we are with this instrument and what our plans are for making use of it. I'd like to acknowledge all the contributions of the team members for this project listed here. So this project is about, again, understanding ice sheet and focused on their dynamics, improving modeling of how ice sheets are expected to evolve over time. We've heard about a lot of different remote sensing methods and different properties of ice sheets that can be measured by remote sensing, but temperature of the ice sheet inside the ice sheet is not one that's been easily available before. In the past, we get ice sheet internal temperature information just from measuring the core sides, drilling deep cores into the ice sheet. It'd be nice if we could remote sense that somehow over larger spatial scales. In particular, because the temperature influences the stiffness of the ice, which then influences its dynamics as it evolves. So a kind of sensor that can measure temperature information is a microwave radiometer. So this project is about trying to see if we can make a microwave radiometer that can measure the temperatures inside of an ice sheet. So the instrument that's been defined is called the Ultra Wideband Software Defined Radiometer, UWBRAD. And if you think about how you might do this, you need lower frequencies to penetrate into the ice sheet, and you probably need multiple frequencies in order to be able to see potentially different layers inside the ice sheet. So we're using a multi-frequency radiometer between 500 megahertz and 2 gigahertz to try and do this. Now that's operating outside the bands usually used for microwave radiometry, so interference is a big concern here. We have to design the instrument to try to work in that kind of an environment. So we decided to sample the entire bandwidth that it's observing and try to do detection of interferers and use of unoccupied spectrum. This is an instrument incubator program supported by NASA, and we're building the instrument now, and still at an early stage here, but we are planning to deploy this system at the Dome C Tower operated by CNR in this coming season, and also fly it over Greenland in spring 2016. And our goal there will be to try and retrieve internal ice sheet temperature information, compare it with core site measurements. So here's a few properties of the instruments over here in this table. It's basically, as I said, a multi-channel radiometer. It just observes at nadir. We're only using a single angle here, single polarization to be flown at an altitude such that we get about 1 kilometer spatial resolution on the ground in the flights. It has a relatively long integration time, a low gain antenna because we preferred to have an ultra wideband antenna for which the pattern would be fixed across frequency in this application. And so there's a few other properties listed in the table there. We set some science goals. We're trying to convince ourselves we can achieve these goals, but this is what we're shooting for with this instrument. We want to try and measure the ice sheet temperature just 10 meters down into the ice sheet because that's an important climate type parameter. We also want to try and measure much deeper into these very thick ice sheets, something like the depth average temperature, for example. But our ultimate goal, if we can do it, is to try and retrieve the profile itself, or at least some model of the profile itself throughout the ice sheet. And the science requirement here is about a 10 kilometer spatial resolution. So we do have some leeway between our, we think we're going to get 1 kilometer, and if we don't meet our requirements, we can spatially average some more and see if we can do better. There's been a lot of interest recent past few years about the signatures that have been seen from the L-band radiometers currently in orbit over thick ice sheets, for example, from SMOS. And it's interesting, for example, the single frequency measurement of SMOS shows an anomaly here. This is a monthly average Antarctic cut here across Lake Vostok in Antarctica. And you see an anomaly of the SMOS brightness temperature decreasing there, which is kind of surprising. There's a lake underneath the ice sheet there, Lake Vostok, but it's below about 3 kilometers of ice. So it's very unlikely that SMOS is seeing the water at the bottom of the ice sheet. Rather, what it's seeing is a change in the internal temperature properties of the ice. And there's been some work, Giovanni's written a nice paper about trying to model this and seeing that, again, we believe this is related to the internal temperature profiles within the ice sheet. Again, giving us some motivation for our project. So I'm going to talk here about some simulation studies we did to try and design the instrument, which are ongoing. We're continuing to try and refine things, convince ourselves we can do this, and about where the system is with building it and what our plans are going forward. So, starting from a modeling point of view, we have a big modeling and retrieval team part of the program. We start off with a pretty simple description of the temperature inside the ice sheet, like a zeroth order type model, which is not necessarily perfect, but it gives us some structure to what we expect about the temperatures, how they might look. And the plot there is of some example temperature profiles on an ice sheet for varying ice thicknesses and surface mass balances and so on. And you can see typically the temperature profile tends to increase with depth. It's driven by, there's a surface temperature boundary condition and a geothermal heat flux at the surface of the Earth boundary condition. So we use this sort of model to help constrain the retrievals. We've been doing a lot of simulation studies, putting in the parameters of that temperature model. For example, the ice sheet thickness, the basal heat flux, the surface temperature, the accumulation rate, and so on. We try and gather whatever ancillary information there is out there to do our simulation studies. And we're simulating a flight path over Greenland there as shown. We're focusing here on the very cold, dry portions of the ice sheet to make lives easier for ourselves in this first demonstration of this kind of instrument. So putting all those parameters together, we then can try and simulate what we think the instrument is going to see using a variety of models. Again, we have a whole team with comparing different models, incoherent, coherent models, more simple models, and so on. Putting all those together over Greenland, we show this is a simulation over here of the brightness temperature as a function of frequency and range as we fly over this path. The edges here are at the less cold parts of the ice sheet, and again we can see what these signatures look like to try and assess how well we think we're going to retrieve the science goals that we have. We also intercompare with SMOS data and SMAP data to try and assess how well our modeling is working. So here's another example of doing that. One thing I should point out is that we're going to have experiments both in Antarctica from the Dome Sea tower as well as over Greenland. It turns out those two are very different for this application. In Antarctica, the low accumulation rate results in much more rapid increases in temperature as you go down in depth, which for us results in the main thing we're going to be measuring here, the brightness temperature versus frequency. So if we simulate those kind of curves in Antarctica for some variations about the temperature profiles we expect, it turns out we get a significant signal versus frequency here. You can see the brightness temperature is changing on the order of 30, 40 kelvins across frequency. And that's, as we go to lower frequencies, we see deeper into the ice sheet. The ice is warmer down there, so you see a higher brightness temperature. On the other hand, in Greenland, the higher accumulation rates result in a sort of more uniform temperature profile versus depth. So it turns out in Greenland, the temperature is more uniform and increases only further down into the ice sheet, which gives us much flatter brightness temperatures versus frequency, as shown here. This is brightness temperature versus frequency in Antarctica up here and in Greenland down here. So we do have a smaller signature in Greenland. It's definitely going to be a more challenging case. However, that smaller signature corresponds to the fact that the temperature profile itself is more uniform versus depth, which is what we're trying to sense. So there's nothing necessarily wrong with that, but it will be a smaller signature that we'll be looking for, which places more requirements. We have to really convince ourselves we've calibrated the instrument well to measure those kind of small signatures. So we did do some retrieval studies, and I think throughout IGARSS here we've had a few different presentations and different sessions about different retrieval studies that have been going on. This is one retrieval study where we generated some Greenland-like measurements, synthetic measurements for some perturbations about expected temperature profile behaviors, and then analyzed how well we think we may be able to retrieve the science information we're after. And we found out in this is a very initial simulation. We found in this initial simulation it looked like we could do a reasonable job of meeting our science requirements and even meeting our goal of trying to sense profile information. But again, the project is continuing to perform these studies and add more fidelity into these simulation studies and assess how well we think we're really going to do it. Also, a variety of retrieval processes are being examined, and there's another talk this afternoon about looking at those kind of studies. So just a quick overview of the kind of modeling work that's going on. Again, multiple talks through IGARSS on this subject, and if you have more questions about those, I'll be happy to discuss with you outside the session here. So on the other hand, we're also building the instrument in parallel with those studies, and it's a radiometer, a multi-frequency radiometer, so it has three main subsystems. a front end and down conversion section, and then a digital back end, and then an antenna subsection. So walking through those, the front end, it has to operate between 500 megahertz and 2 gigahertz, perform radiometric observations. It's a little bit different radiometer design because to avoid the need for wideband isolators up here, it's wideband is what's different from the traditional radiometer. So we chose this sort of hybrid approach in radiometry that's a few other missions have followed, in which you don't have a Dickey switching process directly. You have a combination of antenna and reference road looks simultaneously that go through this so-called hybrid radiometer design, and then you can still calibrate the system. It's a little bit more complicated calibration process. So here's the front end section, which is common across 500 megahertz to 2 gigahertz, and then this gets divided into the individual IF channels. We take that 1500 megahertz bandwidth and we break it into individual 100 megahertz channels that then go into the digital backend. We do have channel definition filters here for each, RF channel definition filters for each channel, because again, we have to worry about the interference environment, so we try to keep interference in one band from corrupting measurements in another band. So we have, in the end, we run up for the airborne deployment, we're going to have 12 channels, it turns out. We originally were planning to have 1500 megahertz channels to make the 1.5 gigahertz, but as we did some more design studies, we decided to reduce that to 12 channels, and in particular 12 because there's some DME equipment on board the aircraft that would probably make that band unworkable for us. So that's our current frequency plan, and the front end, we're doing sort of a stage development here. First, we're building a 4-channel unit before we build the final 12-channel unit. The 4-channel unit is shown here. This is the common front end, and these are 2 down converter boxes, each down converter box doing 2 IF channels. There's an upper sideband and a lower sideband in each box. And so we've got our 4-channel unit put together, and we're working on testing that to ship it out to the tower at Dome C in a few weeks here. Following that front end, we have a digital back end because, again, we want to sample the entire bandwidth and try to do real-time processing of RFI, try to identify parts of the spectrum we think we can use to do radiometric observations. And instead of doing an FPGA or a firmware type thing, we just decided to do a software-defined or software-based receiver. The digital backend is just a PC card that can sample 2 channels in parallel. So it's a 250 megasample a second, 16-bit A to D board, plugged into a computer. Each board can handle 2 channels. So if we want 12 channels, we need 6 boards. It turns out 1 computer can host 2 of these boards, so we need 3 computers to host the 6 boards to host the 12 channels. And so we've got that up and running now, and finalizing the software again for use in our first deployment. Again, as I said, for the antenna, we wanted to have a pattern that was uniform versus frequency, so that all of our frequencies would be looking at the same piece of ice sheet when we try to do our retrievals. We didn't have a big requirement on spatial resolution here because we can fly relatively low altitude, so we don't have to have a very high gain antenna. So when you look at those kind of requirements, we came up with this logarithmic spiral antenna here, which is shown here. It's an antenna that's fairly frequency independent. It can be well matched across that band. The beam width, the gain is about 10 dB. It's a 60 degree wide pattern, which is somewhat wide. If we could have a higher gain, a little higher gain might be preferable here, but with the accommodation requirements on the aircraft and that sort of thing, this is where we wound up. We built this antenna. It's been tested both in an indoor and outdoor range. These are some measured patterns at 500 megahertz and at 2 gigahertz, showing as we desire that the pattern is fairly uniform versus frequency, helping us with our retrievals and making sure things are, again, we're looking at the same place for each frequency. So as I said, the experiment plans going forward, we built this 4-channel prototype. It's currently being tested in the lab, and we will be shipping it to Dome C, Antarctica for a campaign this coming November through January. It'll be placed on the tower that houses the Dome X radiometer operated by CNR. Looks like we're going to be placing it a little bit below the Domex radiometer. It will be co-observing with the Domex radiometer. For the aircraft deployment, we're going to be looking at nadir, but for the tower deployment, we don't want to look straight down at the tower, so we're going to look at off at 45 degrees here. And you know, as I said, it's desirable for us to be in Antarctica because we expect to see this large signature versus frequency. So really our first result we're hoping to get out of this campaign is that we see that significant change in brightness temperature with higher brightness temperatures at lower frequencies. And then we'll also be trying to see if we can use that to retrieve temperature information. So we've got to ship this to our colleagues, Giovanni's group, by August 15th to meet the deadline. So we're trying to make sure we meet that deadline and get the system ready to operate there. After that, next spring, we'll be deploying in Greenland from an airborne campaign, in this case looking at nadir and using the DC-3 Basler aircraft, a Kim Bork. We budgeted this is an IIP project which gives you only a moderate amount of flight time to validate your instrument. So we got about 40 flight hours, and we'll be taking this flight path here, most likely starting northern Greenland and coming down through the cold portions of the ice sheet and then working our way back out. We will see some of the warmer parts as well. We may have the opportunity to try and look for some of the aquifers that are known to exist. That'll be interesting as well, but again, our main goal here is to overfly these core sites where we have deep temperature profiles and try to do retrievals and see how well we can match up with those. If we're successful, then we can try to make a map here of the temperature information across that portion of the flight log. Okay, so that's my talk. You know, we do think the whole project is about the idea that multi-frequency brightness temperatures can give information about internal ice sheet temperature properties. We don't have evidence of that in the past, so it's an idea that remains to be shown by doing this instrument and testing it out. We're about ready to deploy to Dome C, and hopefully next IGARSS we can talk about results from that measurement. And we're also working towards the deployment of the full Dome C. Will just have 4 frequency channels, 2 at the lower end of the band, 2 at the higher end of the band. But Greenland flights will have the entire set of 12 channels. So thank you very much.